Good evening, everyone. My name is Nathaniel Arnold, and today we're going to be going over my Chapter 7 Teach the Doc for bond types and polarity. So for the first question here, we have classified the following bonds as polar or non-polar, and then using their respective symbols for indicating the polarity. So for the first one, we have FCl, which I rewrote here. F, the electronegativity is 4, which is greater than the 2.5, which is the electronegativity of chlorine. So therefore it is polar, and it is negative towards the fluorine due to the higher electronegativity, and negative towards the chlorine or fluoride. We then go over to carbon and sulfur, which I rewrote here, which both have an electronegativity of 2.5, therefore it is non-polar. Go to hydrogen and bromine, which hydrogen has an electronegativity of 2.1 compared to the 2.8, therefore it is polar, and the negative goes towards the greater electronegativity, which is the bromine. We have the same thing for bromine and hydrogen, B and hydrogen, where the hydrogen had a greater electronegativity, and therefore it has the negative charge, a slightly more negative charge, and it's polar. Then we have chlorine and sulfur, where the electronegativity of 3 for the chlorine compared to the 2.5 of sulfur, therefore it is polar, and the negative side is the chlorine. We then move down to question 2, which has us drawing the Lewis structures for carbon dioxide and hydrogen, or hydrogen dihydrogen monoxide, and then determining whether they're polar or not. And so we draw out the linear carbon dioxide, and it is non-polar due to linearity. So the electronegativities cancel out because it is symmetrical here. Then we look at the the dihydrogen monoxide, and we see that it is not linear due to our table that we have here of the number of lone pairs, which we'll be referring to this later, but we know that it is tetrahedral, yes, that is tetrahedral, and therefore it is polar due to the differing electronegativities in tetrahedral shape. So therefore the negative is towards the oxygen as it has the greater electronegativity. We then look at another linear molecule here in question 3, HCl. However, this is polar because of the lack of symmetry, and so therefore it is, while it is linear, it does not have that symmetry, so like the carbon dioxide has in question 2, where it cancels out. We then have this table, which we go to the periodic table and look at the number of valence electrons, and then just practice our ability to do Lewis dots. So for the principle, you'll see here going forward, this is essentially just increasing order or increasing number of valence electrons. And as we increase, we will first go all the way around the atom before adding pairs of electrons. So we will then add a pair once we get to 5, and then add pairs as we continue to count up until we have fully saturated or fully saturated in electrons here. We then move on to finding the number of valence electrons in each of the following substances. So in order to do this, we calculate, or are essentially adding up the number of atoms, valence electrons. So sulfur has 6, chlorine has 7, but there's 2 chlorine atoms, so we multiply that by 2 and get 14 for a total of 20 valence electrons. For hydrogen, carbon, and nitrogen, compound containing all of those, then we have 1 from hydrogen, 4 from carbon, and 5 from nitrogen. That gives us a total of 10 valence electrons. And for the SO4 we have 6 coming from sulfur, 6 coming from oxygen, but 4 times, so we multiply it by 4, and then we have a total of 24 from oxygen. However, we have this net negative charge of -2, which means that we have 2 extra electrons in this substance. So therefore, we're adding another 2 electrons because of that -2 charge, which gives us a total of 32 valence electrons. And then move on to formal charges, where we know that the formal charge of an atom is the number of valence electrons minus the number of lone electrons plus half the number of bonding electrons. Those are in parentheses, so therefore it's valence electrons minus all of this. And I abbreviated it just to make it a little easier for the next question, where we're finding the formal charges for both carbon and oxygen in the molecule or in the compound here. And so for the final charge, we have valence electrons minus lone electrons minus half of bonding electrons. So for carbon, we have 4 valence electrons minus 2 of the lone electrons minus half of the 6 electrons we see here being shared. So therefore it's a total of 3. So then we add these up and we get 5. So it's 4 minus 5, and carbon is minus 1 for the formal charge. Oxygen is 6 valence electrons, so therefore we're doing 6 minus 5 here. We get a positive 1. Now for this chart, we're just looking at the Lewis dot structure for these atoms by looking at the valence electrons on the periodic table, writing the elements, and then finding the shape according to the tables that have been given to us in our book. And so using this table, we're able to find the different shapes of these different molecules. So here we have, for example, hydrogen or dihydrogen monoxide with 2 lone pairs, as we see here, due to the number of valence electrons, and therefore we then go ahead and find it where it is number of electron, or we have 2 lone pairs, and we have a total of those 3, and so therefore, so therefore it is angular. So we can go ahead and do that. Same thing for the BF3, where we have 0 pairs of extra electrons, and we have the 3 extra atoms, so therefore it is the trigonal planes. So, and we can see that right here. So the trigonal planes is the 0 electrons with the number of electron pairs, which is 3. See that there. All right, and we essentially do repeat this pattern of looking at the number of lone pairs by first looking at the valence electrons, and then we will make sure that they are sharing enough valence electrons to make sure that each atom is fully satisfied with a total of 8 after counting both of them that are being shared, and then we find them on their respective position on the chart. So for the next chart here, we were going through and doing essentially the same thing, where we were going through various examples and using the chart to be able to figure out the number of bonding groups in the electrons and the number of pairs of electrons. And so for our first example of carbon dioxide, we know that it has a linear shape from earlier questions, and we know also that it has 2 bonding groups of electrons. For the BCl3, we know there are 3 and there are 0 pairs of electrons, and therefore we can go back here and we can find which one of these that it matches up with, and that would be the trigonal planar. And we would, repeat this pattern for the rest of this chart, as we would go about finding the number of electron groups along with the number of bonding groups by looking up their valence electrons and how their Lewis structure would be formed.